Any other submissions for the project? Maps? All right. Well, I'm looking forward to reviewing those. Hopefully it went okay. We're going to go into the next phase of the project with a brief demonstration today of how to do the reservoir sizing calculations. And so once you finish the homework assignments due for Monday, you can turn your attention to that. You've got plenty of time. It's not due until the Monday after spring break. So the 25th is when I'll collect your calculations having to do with the reservoir sizing. And that'll be the last intermediate submission for the project. After that, I think the project itself is due on April 5th, if I remember correctly, from the handout. It's on the main handout. But we'll talk more about the final submission and what I'm hoping will be in that. After the reservoir sizing demonstration, we're going to move into Chapter 12 topics, so hopefully you're keeping up on reading the text. There's some really good, important information in there, and it'll help you a lot to review the concepts as they're described in the book. So remember that what you have done so far with the reservoir is you've taken a look at what sort of pressures are going to result in the system on account of the elevation that the reservoir is placed at. You want to have the reservoir as high up on the hill as possible because that's going to enable you to use smaller pipes. A smaller pipe will yield more head loss, but if the reservoir is high up on the hill, then that pressurizes the network as much as possible, and it makes the head losses less worrisome. It makes it so that when there is a lot of head loss, you're still not going below the minimum pressure of 240 kPa. But you don't want the reservoir to be too high because then when the flow rates are really low, the pressures could be too big. So you've already played around with those relationships. Another function of the reservoir besides pressurizing the network is to provide a little bit of a buffer during the peak demand times. When demand is very high, then the flow rates are going to be larger for the network than can be supplied by the spring that's used. The water is actually coming from an artesian well up on the top of the hill where the flow rate out there is defined as your average daily flow. And so we're going to consider an example that illustrates how you answer the question, how big should that tank be? And it starts off by using the temporal distribution that's already been distributed, and I think you've also already had to submit your digitization of that curve there, similar to what I've got here. You identify what the actual number is and then the percent of the peak so that we have some 100% of peak flow at the 7 o'clock hour, the 8 o'clock hour. There's a little bit of plateau there. And whatever you decide your design flow rate is, that's defined as the peak flow at the top. And so all of the other flow rates during the day are just pegged to that as a ratio. Well, the procedure that you use in finding out how big should the reservoir be starts off by looking at when is the flow rate out at night less than the flow rate in to the reservoir. The flow rate into the reservoir is constant. It's the average daily flow. But the flow rate out of the reservoir is variable. And so what you'll be doing is for each hourly time increment, calculating how much volume came in, how much volume went out, and it's a mass balance. And over time, you'll calculate the cumulative difference because the tank has to be full at some point of the day, and then the tank levels start to fall and is being drawn down during the day. And just right at the moment before the tank is empty, then it begins to fill again. That's the definition of the minimum size of the tank that's needed in terms of its storage volume. And so this is the three-step process that we're going to be going through, starting with this scale that you previously generated for yourself. So I'm going to move to Excel, and we'll take a look at the sorting procedure that's required to do that. Starting off with the inflow of 253.7. Let's say that that was my average daily flow. Now your inflow doesn't have to be equal to the average daily flow, but just coincidentally, it just so happens that this spring that you've got in your project is providing a flow that's equal to your average daily demand during the peak day. So that's a wonderful coincidence that, that they're actually not demanding more than is available, because potentially a city can grow so large that they are demanding more water than can be available from any given spring. And in places where that happens, then they'll have to pipe in water from other places or maybe desalinate water and so forth. But in this case, they're so fortunate that the average daily flow is equal to what the spring can generate. And so that's the flow rate in. And the peak demand of 400, that is the demand that they're seeing here at the design flow rate. And so my first step is to find out the flow rate out of the reservoir. And so the flow rate out of the reservoir is just going to be this percent of peak multiplied by the peak demand. And it is in liters per second. Okay, so now I know it for each hour of the day. And I can find the flow rate into the reservoir in terms of liters per second. It's constant. It's always just this inflow amount. Okay. The next thing I want to do is I want to try and find when does the reservoir start to fill in the evening. And so let's take a look at, let's compare the out versus the in. The out is much bigger than the in during the evening. And if we look at the chart and try and figure out why that is, remember that the flow rate into the reservoir is just our average value. And so if I was going to draw a line on where that average value is, the average flow rate for the day is something like this, approximately. And so what that means is that anytime the demand is larger, the flow out is larger than the flow in, then the tank would be draining. And anytime the flow into the tank is greater than the flow out, then the water is accumulating inside of the reservoir. And so in the evening, I want to find out when does it cross over. Like when does that reservoir start to fill in the evening? And so I'll compare 7 o'clock. This is my flow rate out. This is the flow rate in. And so, no, it's still draining at 7. The reservoir is still draining at 8. Still draining at 9, at 10. But at 11 o'clock, finally the reservoir begins to fill because the flow rate in is greater than the flow rate out. So what I'm going to do is I'm going to select this, and I'm actually going to put it at the top of the list. Now, it's just coincidentally that it's that large. Okay, so I'm going to move that up here because what I want to do is I want to start off with filling the reservoir and then drawing it down through the day. Now that I've sorted it so that that top one is the one at the top of the list is when the reservoir starts to fill. Now I'm going to find the volume out in terms of liters for each hour, the volume in, how many liters went into the tank during the hour. Okay, so it's just going to be the flow rate out times however many seconds are in an hour. 60 seconds per minute times 60 minutes per hour. So that tells me how many liters. That's kind of a big unwieldy number, and so what I should do is maybe change it to cubic meters. And so it's that same thing, but now divided by 1,000. So this is how many cubic meters accumulate in the hour. So the volume in is going to be the same thing. If I just drag over, now it is looking at the flow rate in. All right. So any questions so far of what we've got on screen? So I know how much goes out and how much goes in. The next thing is to find the difference for each of them. And ds dt is just saying the change in storage with respect to time, and that's cubic meters. So that would be the volume in minus the volume out. So that is how much net accumulation was inside the reservoir during that time. And so when it's positive, that means the reservoir is filling. When it's negative, that means that the reservoir is emptying. And there's this nighttime period where it fills up a lot, and then in the morning rush, the reservoir gets drained a little bit. And then in the afternoon, when nobody's home, the reservoir recovers a little bit. It's filling for just a little while. And then there's the evening rush when the reservoir starts to drain a lot, nearly empty. Okay, so that's why it's sometimes positive and sometimes negative. And the last thing is the accumulated storage volume. And that's in cubic meters. Okay, so how much has accumulated inside the reservoir during the first hour? It's just equal to this amount. Now, at the end of this next hour, how much is in the reservoir? It is however much was in there in the previous hour plus the hour in question. And so then we can drag that down and find out how much is in the reservoir at 1 a.m., 2 a.m., and so forth. So now you'll see that it actually decreased a little bit because there is more going out and coming in, and so the accumulated storage volume is going to get a bit smaller. I'll drag it all the way to the end now. Okay, so the reservoir's filling, it's draining, it's filling again. What we want to do is see, number one, that it goes to 0, because what that means is that at the end of this 10 o'clock hour, the reservoir is empty, which is what we want it to do before it starts filling again. We don't want to make the reservoir any bigger than it has to be. And we could have made it twice the size, and there'd just be some extra water in there at the end of this cycle. But the reservoir size that's needed, we need to go through and find out which one of these is the maximum. And just to make it easy to identify where that is, we'll just say max, and that'll return. We're looking for the one that says 2503. So the 2503, it's right there. Oops. So this is the maximum. That's how full the tank gets. And so we should build the container around that volume of water equal to that volume so that that much water can be stored. If we have that much water in a tank, then it won't run dry during the peak demand part of the day. Maybe we'll make the tank a little bit larger just as a safety factor, 20%, 25%, something like that.
What kind of number do you want us to round to? The closest 50 meters cubed, 100 meters cubed? Do you want an exact number?
Use the exact number and build in a safety factor of 20%. But then the pricing that goes along with it, you should interpolate. I mentioned the size of a couple of reservoirs, so don't round to those sizes. Just use those as an indication. Create like a model using that data for what the cost will be as a function of volume. Yeah. Other questions? All right. Well, that is how you size a reservoir, and you'll see this sort of thing again. This is when the reservoir that we just analyzed had in constant and out is variable. And so this was drinking water. Can you think of a situation where you may see what's coming into the tank be variable and you'd want the out to be constant? Do you have any idea where such an occasion may arise?
If you got something instead of our rain, it's going to be variable input.
Okay, yeah. So a stormwater runoff could be variable input, and that's absolutely true. Usually in a storm, there will be this peak, and then it'll taper off where it'll slowly drain the watershed for a while. And maybe if you are discharging to a river that you don't want to suddenly have its water levels rise, maybe you'd prefer that the outflow is constant. And so one situation where you'll have a case like this is a stormwater pond. And the analysis and design procedure is the same. The similar thing where you're looking at the incremental volume during each hour or during each time step. Another case, besides a stormwater pond, might be with wastewater. People are using this water and at a variable rate, and so they're flushing their toilets, they're running the shower, and so they're going to be sending water to the sewer at a variable rate. But the treatment plant, the bugs and bacteria that break down waste and wastewater, they don't like these huge changes in flow rate and organic loadings. It's more efficient to have a steady waste stream being treated. And so flow equalization basins are also sized using the same approach of incremental volume balancing.
Dr. Wade?
Mm-hmm.
Just to review, I was taking down some notes as you were doing this, but the formulas for volume are...
It's just the flow rate times how much time is in the increment in question. So what I did was it was the flow rate times 3,600 because that's how many seconds is in an hour.
And DSDT?
Well, that is the difference between the volume in and the volume out.
Oh, okay. Makes sense.
All right. Did you have another question?
No, just thank you.
Okay, sure. Next, we're going to take a look at specific energy. And specific energy is talking about how much energy there is relative to the bottom of a channel. So it's neglecting the delta Z component in total energy. And specific energy can be calculated either in terms of the velocity in the channel, if that's known. Sometimes we don't know the velocity, but we do know the flow rate and the total cross-sectional area. And so we can make that same substitution that we saw previously in the closed conduit part of the section of the course. But consider some rectangular channel that's 4 meters wide, and there is 10 cubic meters per second that needs to go through that channel. So how many different combinations of velocity and depth are there that could convey that flow? Remember that Q equals VA. And so what I'm saying is there's going to be 10 cubic meters per second going through the channel, and the area is going to be 4 times Y. So how many combinations of velocity and depth are there that can convey that flow? It's an infinite number. It might be that what is going through the channel is a very small depth. So what if Y is small? Well then, V would have to be fast in order to get 10 cubic meters per second. Or it could be that you've got a very full channel and Y is big, and therefore V would be slow. To get 10 cubic meters per second, if it's really deep, then it would be slow-moving water. And so the point is that there's this infinite number of combinations. I've just listed some of them here, where you've got a lot of different velocities. We can calculate what the area would be for those velocities, because the area is going to be the flow rate divided by the velocity. The depth is a function of the bottom width. We know the bottom width in this example is 4 meters, and so if there's a certain area that there has to be, then we can find out what is the depth. And then energy is calculating the depth plus the flow rate squared divided by 2GA squared. So what I'd like you to do is calculate, I've got them for most of them, but I'd like you to calculate the blanks for the 3 rows that have green arrows on them, just to get some practice calculating specific energy. And then we're going to look at what this data means. So to this 4-meter wide channel, you can find the areas, the depths, and then the specific energy for each of them. If we look at the formula, specific energy comes from two components. It comes from the depth, and we can think of that maybe as potential energy. And then it also comes from the velocity head term. Okay, depth and velocity. And so when we have this velocity of 10 meters per second, the energy is 5.3 meters, but the depth only is contributing 0.25 meters to that. And so for that top row, where the velocity is 10, most of the energy came from the velocity head term. Most of the energy is like kinetic energy. Most of that 5.3 meters. But then down here at the bottom, where the velocity is really slow, but we've got a large depth, 2.5 meters, well, the total energy is 2.55, and the majority of that energy is coming from the depth. And so what you can look at in this energy column is you think about that there's this one extreme where the energy is coming from a really high velocity, and the other extreme where the majority of the energy is coming from a deep depth. And what you'll notice is that there are places, 2.55 is our energy here. Well, there's also going to be another place up in this zone between these two readings, between the 6 meters per second row and the 7 meter per second row, where there's going to be also another 2.55 meters of energy. And so this isn't just a line, it's actually a curve where if we want to take a look at flow depth versus velocity, this is the relationship. But a far more interesting thing for us to graph is specific energy versus depth of flow. And we're going to spend a lot of time looking at this figure and figures like it. Understanding this figure is a big idea. This is like a multi-day idea. Although it's a simple graph, I mean, all we've drawn is the specific energy, and you saw the table of how that was calculated, and the depth of flow associated with that specific energy. And so remember we talked about the case when it was 2.5 was the depth. So up here is the velocity fast or the velocity slow. Okay, 2.5, right, slow. That's when we've got lots of depth, but the water's just ambling along. It's just very, very slow moving. And we have the total energy was about 2.55, okay? So there's this extreme, it's got a lot of energy because it's very deep. And then there's this other extreme where there's a lot of energy, and why is there a lot of energy? Where is it coming from? Velocity, right. So what about this point right here? Well, this is the minimum energy. And the reason why I had you calculate the total specific energy at a velocity of 2.905, I mean, that's not a very round number. I picked that specifically because I knew that's the velocity associated with the lowest specific energy. And so that's sort of a special thing, the lowest specific energy. And if you think about the definition of the word efficiency, something that's highly efficient is something that can do its work with a little amount of energy. And so all of these are different energy levels for conveying 10 cubic meters per second. But this one, it's the least specific energy associated with conveying the same 10 cubic meters per second. And so you could say that this is the most efficient flow. This is the flow where you're getting the most flow rate for how much energy exists inside of the flow. So it's not like energy is being added to the flow. That's just how much energy is in the water as it's moving, as a function of its depth or its velocity. Okay, so back to this graph. So what that means is that for some certain amount of specific energy, there are two different depths that are associated with that same amount of energy.
Is that chart just for that one scenario?
Yes, good question. We can draw a different chart for any other scenario, But this is for 10 cubic meters per second, channel width of 4, and let's see, flow rate of 10, channel width of 4. And if any parameter changed, we'd have a different figure. They all have a characteristic shape, though. They all look very similar to this. They won't have radically different shapes, but they would have a different minimum energy amount, or they'd have a different minimum. There's a certain depth that's associated with this minimum of energy amount. And that depth is called the critical depth. The critical depth. Remember that you've classified already supercritical flow and subcritical flow. Well, you didn't know it then when you calculated it the first time, the Froude numbers, but the subcritical flow is any time the depth of the water is deeper than this critical depth. And so this is the subcritical region because the water is moving slow, subcritical. Below this line, if the depth is lower than the critical depth, this is the supercritical region, supercritical flow. So what is actually governing what depth the flow is at? Well, that's a factor of the channel geometry, the roughness of the material that's used. But for any particular fixed material, fixed width, like why is it that the water would maybe be, why would sometimes the water be fast but shallow compared to other times it would be deep and slow? The thing that would change between these two cases is the slope. The slope is what determines the flow depth. Okay, so the critical things for you to know, the really important concepts, is that there is some special depth, and when the flow is deeper than that, the conditions are subcritical, and when the flow is shallower than that, it's supercritical. And what actually governs what the depth is going to be is how steep the slope is. So the criteria is the Froude number. That's how you can calculate whether conditions are supercritical or subcritical. One way to distinguish is the Froude number. The other is to calculate the critical depth and compare it to the depth that you're actually measuring out in the field. And then that you can also classify whether conditions are supercritical or subcritical based on those measurements. Sometimes the top width changes as a function of depth, as in the case of a trapezoidal channel. In a rectangular channel, it doesn't matter what the depth is. The top width is always going to be the same. You know, as the depth goes up and down, it's always going to be 4 meters at the top for a rectangular channel. But for a trapezoidal channel, that's not true. You know, the deeper it gets, the higher width you've got along the top width. And so, in addition to critical depth, we can talk about what is the top width under critical conditions. And you need to know that for one of the ways you can calculate Froude number is taking into account the flow rate, the top width, the cross-sectional area, and G. So both of these are ways that you can calculate the Froude number. And you've seen, I think, this one before. You found the Froude number was the square root of it. But because the channel is trapezoidal, in some cases, it's easier to speak in terms of the flow rate and the top width, depending on the geometry. Either one of these will always give you the right Froude number. There are certain equations that you'll see for Froude number that are only valid for a rectangular, section. Other formulas that are only valid for a rectangular section that's very wide, but these will always give you the right answer. And the criteria for Froude number is when it's less than 1, conditions are subcritical. When it's more than 1, flow is supercritical. Okay. So I'd like you to practice using the Froude number to determine whether flow is subcritical or supercritical. And we could do that graphically because you've already had a sneak peek at what is the critical depth. But we'll revisit that critical depth method of distinguishing the flow regime in a minute. For now, I'd like you to calculate the Froude number of each. Yeah.
What was the relationship between the depth and steepness, the images?
It's the slope that causes the depth to be a certain thing. The slope determines depth. Froude number greater than 1 means supercritical. So when the depth is 0.25 meters, that's in this range down below here where we've got fast velocity that's causing the high specific energy. So anytime the depth is less than the critical depth, supercritical conditions. What would cause it to be supercritical? A steep slope. So let me write that. Depth is less than YC, then that is supercritical. What caused that would be that the slope is greater than some critical slope. A steep slope causes shallow depths and fast water. A steep slope. The other way that we knew that this was supercritical was because the Froude number is greater than 1. The Froude number we got was 6.38. Okay? The other condition where the Froude number was less than 1, so the Froude number was less than 1, that's going to be subcritical. The other indicators that it's subcritical is the fact that the flow depth, Y, was greater than YC. Our critical depth here is, about 0.86. Okay? And so in this case, the slope is going to be less than some critical slope. So we've got a shallow slope And an interesting thing, they sometimes, instead of calling it a shallow slope, they call it a mild slope. Mild. Just like salsa. I guess that makes this spicy. They don't say that. But they do call this a mild slope. You've got a mild slope, slow water, and deep flow depth. So any questions or comments about this?
So where would we be concerned with the lowest specific energy, like saying a real world?
When water is moving along and it encounters an obstruction. Ordinarily it would be flowing this deep, but then it comes to an obstruction, the water will pool and a little bit will go over. It'll pool more, but it finally reaches equilibrium again when it can get enough over the obstruction, and it'll be flowing at the critical depth when it does that. And so you will have E minimum as it flows over that obstruction. So that's a real-world example that's very, very important. We'll talk all about that later, but that's your sneak peek of why minimum flow energy is important to us. And the other thing that is really important about this is the most exciting thing I have to show you in the lab. Water's moving along at some flow depth, and then all of a sudden it jumps up to another flow depth, a hydraulic jump. This explains the hydraulic jump, because water is flowing with some shallow flow depth, and then just all of a sudden it pops up to a deeper flow depth. Well, what's the other flow depth going to be? It's going to be the alternate depth on the other side of the specific energy diagram. Oh, that's not it. Is that the last thing in the notes?
Yes.
All right, well, I guess your weekend starts early as far as this class is concerned. All right.